We're about ready to begin. So I want to say welcome, everyone, to today's webinar, which is hosted by the Sea Ice Prediction Network Phase 2, also known as SIPN2. It is facilitated by the Arctic Research Consortium of the US, or ARCUS. And today's ARCUS team includes Stacy Stout, Kuba Genda, Britt Myers, our Executive Director, Helen Wiggins, and me, Betsy Turner-Bogren. Today's presentation is the second in the 2020 SIPN2 webinar series, which is organized by Muyan Wang, a member of the SIPN2 project team. Today's topic, machine learning, challenges and opportunities for applications in sea ice prediction, will be presented by Elizabeth Barnes at Colorado State University, Morteza Karimzadeh at Colorado University Boulder, and Tom Andersson at the British Antarctic Survey Artificial Intelligence Lab. A link to an online survey will be available at the end of today's webinar. We'd appreciate your feedback as well as suggestions for future webinars. Before our presentation begins, we have a couple housekeeping items. Next slide, please. When you entered the meeting via Zoom, your video was switched off and your audio was muted by the host. Please keep your microphone muted to help prevent disruptions and background noise. You may turn your video on. Your Zoom controls, chat, etc., can be found by hovering your mouse over the bottom of your Zoom window. We recommend that you do use the chat feature to chat with individuals or the whole group during the webinar. Next slide, please. Questions will be addressed during the question and answer session following the three presentations. If you are joining by Zoom, please type your questions into the chat window at any time, and I will record them and read them aloud during the Q&A. If you are joining by YouTube live stream, please type your questions in the live chat window. A facilitator, Kuba, will share your questions with me and I will read them aloud. If you are joining by phone, you will need to raise your hand by pressing *9 and unmute yourself by pressing *6 to ask your questions aloud. I will repeat these instructions at the end of the presentations. If needed, the presenters have offered to continue to be available for another 5 to 10 minutes following at the top of the hour to continue questions and answers. If you need technical support today, please contact Stacy Stout via chat or by email, stacey@arcus.org. Next slide, please. This SIPN2 webinar event is organized by Muyan Wang. Muyan is a research scientist at NOAA and the Joint Institute for the Study of Atmosphere at the University of Washington. Muyan, at this point, I'll turn the program over to you.
Thank you, Betsy. Okay, so machine learning, one of the key building blocks of artificial intelligence, has been a part of the technological world since the 1950s, and it is closely related to computational statistics, which focus on making predictions using computers. To improve sea ice forecast skill is one of the objectives of the SIPN2. It is my great pleasure to introduce our three speakers today. Their short bio is shared via the online link in the chat window, which is posted there. So our first speaker is Dr. Elizabeth or Libby Barnes. She's Associate Professor of Atmospheric Science at Colorado State University. She received her Bachelor of Science degree honors in physics and mathematics from the University of Minnesota in 2007 and a PhD in atmospheric science from the University of Washington in 2012. Libby joined the CSU faculty in 2013. She has received several awards from the CSU, and she's also recipient of the Hugh James Horton Junior Scientist Award, National Science Foundation Career Award, and AMS Clarence Leroy Messenger Award. Libby's research is largely focused on climate variability and change and the data analysis tool used to understand it. Her topic of interest includes Earth system predictability, jet stream dynamics, Arctic mid-latitude connections, S2S prediction, and the data science method for Earth system research. Our second speaker, Dr. Morteza Karimzadeh, is an assistant professor in the Department of Geography and affiliated assistant professor in the Department of Information Science at the University of Colorado Boulder. Morteza received his Bachelor of Science in 2008 and a Master of Science in 2011 in Iran, and a PhD in Geographic Information Science from Penn State University in 2018. He joined CU in 2019. Morteza is a geospatial data scientist with research cutting across geographic information retrieval, machine learning, geovisualization, and visual analytics. Our final speaker, the third speaker, is Tom Andersson. Tom is a data scientist at the British Antarctic Survey Artificial Intelligence Lab. He graduated with a double first in information and computer engineering from the University of Cambridge, UK in 2019, holding a master's degree. Tom's research at the British Antarctic Survey involves the application of cutting-edge machine learning algorithms to remote sensing and climate data model data. Specifically, he is to apply explainable deep learning algorithms with 2D satellite and climate simulation data from the Arctic in collaboration with the Alan Turing Institute in London. So now let's hear from our first speaker, Libby. Thank you.
Okay. You can hopefully see my screen and presenter mode. Can someone nod for me? Wonderful. Okay, thank you all for coming. I have the very difficult task, as do all of us, of in 12 minutes have to try and teach you something new, so we'll see how it goes. And I want to tell you about interpretable neural networks for learning new science. And this is really quite a big topic, but in 12 minutes, I hope I sort of whet your appetite to want to learn a bit more. And so I have multiple collaborators in my group working on this talk, and some of their results I am showing today. So many of us in science think of machine learning as a black box. So we have data go into some black box where magic happens and a prediction comes out on the other side. And today, what I will convince you, hopefully, of is that it's really not a black box. These days, visualization tools are constantly coming out of the computer science research world that, in my mind, are a game changer for using machine methods specifically for science. And I'm going to introduce one of those tools today. So to back up a moment, since this is a very broad audience, what is a neural network? And while I can't go into all of the details, I'd like to give you a feeling for the general methodology or architecture of one of these neural networks. So here's how it works. These yellow circles or nodes or units represent the inputs, say different grid points of sea surface temperature. And what we're going to do is that X1, that input, gets multiplied by a W1 or weight. That's what each of those arrows connecting to the blue unit represent. So in this case, what we see is X1 is being multiplied by W1 and summed or added to X2 times W2. And we also add an additional term. The computer science world calls it a bias unit, but we often know it as, say, a y-intercept. And up until this point, we just have multilinear regression. Now, what makes a neural network so powerful is its nonlinearity. And what ends up happening is we take this multilinear regression formulation and push it through a nonlinear function. And that's called F here, or our activation function. And this is where we take it from a linear problem or linear regression problem to a nonlinear one. Now, this activation function can take many forms. Here are some examples found in the literature. And if you'd like, I'm happy to talk more about those during the question and answer session. But ultimately, they add nonlinearity to the system. So the whole idea of training an artificial neural network then, in this setup, is merely determining the W's and the B's that make your prediction most accurate according to some metric that you have decided. So on its own, that may not look very complicated, but now imagine taking these blue circles and the output of one of these activation functions then becomes the input into another unit. And these feed off each other over and over again. And these networks can then get quite complex very, very quickly. And ultimately, the whole goal here is to make a prediction when you get to the end. So for example, you could set it up as a regression problem, or in this case, you could set it up as a classification problem where you're trying to figure out, say, if temperatures over some location in the United States is going to be warmer than average, say average, or cooler than average. So you have 3 different classes in this case, and you're trying to determine which one's most likely given the sea surface temperatures, say today, as an example. So the complexity and nonlinearities of an artificial neural network allow it to learn many different nonlinear pathways of predictable behavior. And once trained, this box, if you will, is made up of weights and biases that can be used for prediction of new data. So that's the idea. But as scientists, we're not used to just making predictions per se, but we also want to know how did this prediction come about? If it's right, why is it right? What was learned? And this is where interpretable AI or explainable AI really comes to bear. So what can we expect from neural network visualization? Well, you can think of it sort of like a black backpack filled with stuff at the airport. Remember airports, oh, so long ago. It goes into an X-ray scanner, and we get a view of what's inside the black backpack. And it's certainly better than no scanner at all, but it's not a perfect representation. And this is the way to think about these neural network visualization tools. They're not perfect views, but they are better than nothing, which is what we were doing before, and allow us to see in a little bit. So there are really 2 types of visualization tools, at least the way I think about it. Type 1, or type A, is feature visualization. And the goal is to understand all internal components of your network. That is, each of these blue units is doing something to the input values, and you seek to understand the meaning of each and every one of these blue units. Now, there are lots of tools out there from the computer science community to do that. What I want to talk about, though, is the second type of visualization, which we call attribution, or explaining the decisions. And the goal here is not to understand each of those individual pieces inside, but to understand the neural network's overall decision-making process. That is, given some input values, why did it make a certain prediction at the end in a general sense, not worrying about the middle. So the particular visualization tool that my group has been using extensively is called layer-wise relevance propagation. And I'm going to first demonstrate it using a classic cat example, and then I'll bring it back to geoscience. So here's an image with a cat in it, and the idea is to set up a network to predict the probability that there's a cat in this image. Now let's say you have a really good network and the probability of a cat comes out at 0.98. Well, that's great, but you might wonder, how did it know it was a cat? Where did it look? How did it know that the cat was in this image? And what this tool does is it takes that value, that 0.98, and it propagates it backwards through the network such that the end result is a heat map showing the regions that were most relevant for the network's decision that it was a cat. Now, the neat thing, and I can't go into details about this now, but the neat thing is that this is this probability here, this 0.98 is conserved. That is, if you sum the heat map over this entire image, it will come out to 0.98. So it's in essence telling you how that 0.98 is distributed in terms of the decision-making process across this input image. So ultimately, you have an input of a cat and figured out it was a cat, and you can go back and ask where the network looked to determine it was a cat. So an example use from their paper, the computer science group that came up with this tool, is let's decide whether there is a horse in a given image. So they're going to use visualization tools to determine the strategy the network used to determine there was a horse. Now I want everyone to look and say, do you think there's a horse in these images? The answer is there's a horse in every single one, all 3. But the question is why? Now as humans, we know there's a horse in these images because we see the horse. But we can ask, how did the network know there was a horse? And we can make these heat maps. And as you can see, the most relevant region for determining there was a horse was not where the horse was, but is actually in this bottom left-hand corner. And it turns out, if you look carefully, that is where the copyright symbol has appeared in each of these images. And what we now learn is that the network, trained over thousands of images, learned that when it sees this specific copyright symbol, there's probably a horse in the picture. Now, as scientists, this is probably not what we want our network to be learning. And so it's important to understand what and how the network is making its predictions in order to find these cases of getting the right answer for the wrong reason. So what does this mean for Earth system prediction research? Well, first, it helps identify problematic strategies, i.e. the right answer for the wrong reasons, like in the horse example. It can also be used to design the machine learning methodology. For example, we have a student trying to use networks to identify clouds and convection. And in using this tool, learned that the network was not using the temperature information at the top of the clouds, and so needed to redesign the network to take that into consideration. Another example is building trust. So your predictions are good, but you want to make sure they're right, again, for the right reasons. An example here is a project I'm working on using Landsat satellite imagery to identify human activity. And the network identifies increased human activity in 2018 compared to 2000. And we can use LRP to show that it's because a road went in the region, and that the network was able to identify that it was the road, this red region here, that made its prediction of human activity increase. So it says, oh, good, it's getting the right answer for the right reason. But finally, I think these tools, and this is where my group is really getting very excited and doing a lot of work, is in discovering new science. That is, when our machine learning method is capable of making an accurate prediction, we can now explore why. That is, where is that predictability coming from? And I think that is where the SIPN2 group may find this work to be of most interest. So we are using this tool to do new science and understand the reason behind the accurate predictions over a range of topics. I've listed them here, but I only have time to show you one quick slide of how we're doing this for multi-year prediction, just as an example, but I'm happy to talk about any of these during the question and answer. So this is work being done by my PhD student, Ben Toms. And the concept is we're going to input sea surface temperature maps from the past, input it into a slightly fancier neural network called a convolutional neural network, and output the prediction of temperature over a location somewhere on the globe. In this case, he's in Alaska, but he's done, you can think about predicting temperature anywhere. And we're going to predict the 5-year average surface temperature at this one grid point, given the past SSTs. So ultimately, he's done this, and the network is quite good and makes quite accurate predictions, but we can now ask why. And so on the left-hand side is an example of an accurate prediction showing the SSTs today, and we are making an accurate prediction for Seattle over the next 5 years. Now that's nice, here are the SSTs, but the question is, did the network use all of these SSTs anomalies to make its prediction? What did it use? And the right-hand side shows the LRP heat map. That is, the brightest colors, these white colors, show where the network put most of its attention in making its accurate Seattle prediction. And we see that while the SSTs are strong in the Atlantic and in the tropical Pacific, it really is focusing on the extratropical Pacific in its predictions. Now, what's also neat about this method is you can make this for different predictions and get different answers. For example, this is another accurate prediction showing that the network has learned that other regions of the globe were important under that regime of making a prediction over Seattle. So the point is that where the network looks can change because of its nonlinearities and complexity of its architecture. So for us, the science is not really about making a multi-year prediction, although that's exciting. It's really identifying the predictable patterns or regimes of the Earth system that lead to predictability. So wrapping up, if I could leave you with 3 thoughts in those 12 minutes, the most basic of neural networks can be viewed as nonlinear regression, and I believe climate scientists really are well equipped to think about this and use these tools. They are no longer black boxes, and tools exist to help visualize their decisions. And in my mind, this completely changes how we can do science with them. And finally, the science can be what the network learns rather than just the prediction. So this has really allowed us to get creative and have a lot of fun. Okay, and with that, since we are waiting to take questions until the end of all speakers, we will hear from Morteza Karimzadeh, and take it away.
Thanks very much. It'll be a very interesting talk. I will be sharing my screen momentarily. All right. Can I get the nod that you can see my slides? Perfect. Well, welcome everyone. I'm going to be talking about visual analytics and interactive labeling for machine learning. My name is Morteza Karimzadeh, assistant professor of geography at the University of Colorado, Boulder. So given that we have only a little bit of time, let's cut to the chase. Let me change my pointer to a laser pointer. This should be a little more helpful. So let's take a look at this generic deep learning model, right? In this case, it looks like a CNN right here, convolutional neural network, and some added layers. We've got our input data, and then we've got the prediction labels here, right? That's the entire thing that machine learning does. When you have the input data as well as a sample of labeled examples, then you can train this model that can do predictions elsewhere, right? But there's a couple of problems here. First of all, a lot of times you actually don't have enough labels, enough data to train your model, right? So that's one problem. The other thing is we mostly focus on training this entire thing all together, which takes a lot of computational resources and time. And in a lot of cases, you're dealing with multi-source data, big data that takes weeks at times for a single model to be trained. So how do we deal with these two problems overall is kind of the focus of my talk, with the primary focus of, well, how do we generate labels, right? It's a chicken and egg problem is in that, hey, I really want some labels to be able to generate labels for unseen data, predictions for unseen data. So how about we actually use a machine learning model to predict some labels, albeit imperfect, and show it to a user, to the expert in the field, and see if we're getting the labels right. And if we are not, then they can maybe correct the labels. But then again, the problem with that is that the model doesn't exist. So the chicken and egg problem again, right? So there's a few solutions in there, but the focus of my talk would be, well, how can we use pre-trained models or fused models that might be trained in other fields for other specific tasks, right? And then use them for our specific task that might be different from the original task. In our case, for instance, in the example that is coming up, I'll show you an example of determining the relevance of a piece of text. Well, there are embedding models for text that are trained for other purposes, but we can add a few layers, shallow layers that are cheap and easy to train on top of the output of these features, and then just iteratively train them as the user labels the data, right? Hopefully it will become more clear as I explain in the follow-up examples. So I have lots of examples in this kinds of work in other fields. I'll show you two, one for real-time social media analytics for situational awareness, the other one for spam bot labeling. And then I'll pivot to our upcoming NSF Earth-Q projects for sea ice mapping and classification, and how we are going to use this approach to solve a geoscience problem. So just a little bit of a background on this social media analytics and response toolkit, reporting toolkit that was screenshot you're seeing here. It's a tool for providing situational awareness to first responders. Let's assume the first responder wants to look at the tweets about wildfire events, right? So the stream of tweets, real-time tweets is coming in. The tool is harvesting those and filtering them and then visualizing them in a set of visualization, topic lenses, word clouds, and individual anonymized messages. But really the problem that this tool had, and we heard that from a lot of first responders, we had this thing has almost 70-something repeat users across the country, is that we still get a lot of noise. We get tweets that are not relevant to our specific case. So how do we train an algorithm that can look at the text, right, and say, well, the entire apartment is burning down is relevant to my wildfire scenario, but, well, Bernie feeling the burn is not quite relevant to a wildfire scenario. How can the system differentiate between these two? And these are dynamic, right? What if I'm looking at the wildfire in this corner and then I go and look at a hurricane that comes in, my definition of relevance changes. Or even a wildfire in one scenario might have a different semantic in terms of relevance to another one. So the solution to this was, again, letting the user to iteratively train and generate those labels. So this kind of approach is good for both when you don't have enough labeled data for training, and also when your application is real time. So what we did was taking those tweet texts, feeding it into a pre-trained model that is already distributed by Google. This takes weeks to train, and then adding a shallow network that we train in real time every time the user, let's say, labels 10 extra tweets as relevant or not relevant, or can decide. And then predicting those labels using the network. If the network gets it wrong, the user goes in, corrects those, and then we retrain this shallow network, right? We're using the power of the pre-trained network. We're not retraining that. But this allows the user to retrain on the fly. And the way we evaluate this model is also a little different, right? In machine learning, you do cross-fault validation. But what we did instead is to look at saying, hey, we have incoming tweets. For each batch of 10 incoming tweets that are labeled by the user, how does our accuracy improve? We see that, after almost 200 labeled tweets, our accuracy kind of stabilizes around between 60 to 80%. But even with less than that, we see a whole lot of improvement in the beginning of the curve to see, well, are we getting the relevance right or not? And this is just the result after 20 clicks. The user is looking at the tweets coming in about an extreme weather event, and they have clicked on 20 tweets as relevant or otherwise, and to see that if we sort based on relevance, these are quite relevant to weather events, and these are quite irrelevant. We've sorted them by lack of relevance, right? So the tool allows us to do that. Another example, again, we have a lot of spam bots on social media. Almost 40% of all accounts on social media across all platforms are spam, right? They spread disinformation, which is a big problem, manipulate public opinion. And it's a huge problem, but the bigger problem that we're dealing with here is that we can't just learn their behavior and label as spam or not. They constantly change their behavior, and also they act as parts of bigger campaigns. So you could go in and label one account as spam, but there is hundreds of accounts that are acting the same way. So how do we view these accounts using a flyby view and label in batches, and also go in and fine-tune and remove or add individual accounts to those batches? There are automated ways of doing this, but again, because the newer campaigns of social media spam bots act as groups and their behavior changes, our solution was to again provide an interactive visual analytics tool for this purpose. So how do we do this? Each tweet comes with a bunch of metadata, including number of tweets from that account, from number of retweets of that account, number of followers, number of followees, number of like tweets, joining dates, right? These are all clues that will help us determine whether an account is a spam bot or not. And again, some of these spam bot campaigns are really smart. They create accounts 2 years in advance just to use it now. So you can't just say, hey, this account was created now, therefore it's spam. We have to have a flyby kind of higher level view to be able to view these, right? So we take all this metadata in addition to the actual tweet text, and then provide integrated linked visualization of all these features in timelines, in dimensionality reduction views, as well as the actual topics on account, posts in, and the distribution of those features for different selected features, right? So what we see here, the green says genuine account, purple means spam bot, and blue means unlabeled, right? And we can see all of those in different views, those colors. So the user can interactively go in and play with these and then find spam bot campaigns. I'll just show you an example. Like we're looking at the timeline in 2014, then we can go and look at the dimensionality reduction view. We see clusters of spam bots, and we can actually go and look into that cluster of accounts and see, well, what topics are they posting? And we can inspect the actual tweet concept and go ahead and label it as spam bot or not. I'll be happy to explain more if there are questions about this. But again, the key to this is that there are pre-trained models in the back, but this can be iteratively trained and updated with new campaigns of spam bot accounts being activated on social media. What we see here right now is that all those features that I showed you, almost 25 of them, reduced to 2 dimensions using TSNE or PCA algorithms so that we can visualize them and find clusters of social spam bots that we can batch label, saying these are most likely spam, these are most likely genuine, and then we can go and look at the individual tweets and accounts to make sure we are not mistakenly labeling an account as spam bot or not. So far, no geoscience, no CIs, but the reason I showed you these 2 examples because I feel like those were the closest to what we are going to be doing for our upcoming NSF-funded project, in which we will do data fusion for CIs classification. As part of this, we'll hopefully be reaching out to you. We are looking for advisory board members to give us feedback as to exactly what to do. So we know there's a lot of data sets out there, but you probably have seen some of these, if not all, and you know that the newer ones especially, it takes maybe a week to just download a piece of data from these. So our hope is to be able to do this featureization, right? This combination of fusion of data sets in the cloud and provide these pre-trained models. In our case, we'll use them for CIS classification. You may use them for, I don't know, CIS glacier discharge, for instance. And then iteratively train this shallow network to be able to generate CIS labels right here and allow the user to iteratively label data, right? And the system becomes better and better. So we show them, we are planning on showing the expert user reduced dimensions so that they can batch label CIs, and as well as the individual views of satellite images or charts in which they can refine their labels. The output of our work essentially will be these pre-trained models, which will be otherwise very expensive and hard to train and fuse all this data that can be used not just for CIS classification and mapping, but other geoscientific purposes, as well as the elusive, non-existent CIS labels, right? Because we have really limited CIS charts right now that we can work with, not quite enough for training predictive machine learning models. And as part of that, we are collaborating with the National Snow and Ice Data Center with Andrew Barrett, Walt Mayer, Srijoda Khalsa. We're really lucky to have them on the team, as well as the computer science department at CU Denver. And I am the lead of the project. We are made the award notification, but we're still not awarded. We're waiting for NSF to give us the go-ahead. But I hope to reach out to you, and if you are interested in being involved and giving us feedback on how to create these tools, we would love to have you on our advisory board. Not a lot of commitment, quarterly meetings in a year online. So 4 meetings a year, not more than that.
Thank you.
With that,
we're right at the end of the 12 minutes. Thanks.
Yeah, we are. I am done with my presentation, so I'd like to invite Tom Andersson to take over.
Thank you.
Awesome. Thank you, Morteza. I'll just share my screen. So hopefully you can see that. Shout if not. I'm just going to start a stopwatch, so I've got a big number blaring at me, which stops me from overrunning.
We do not see your screen yet.
I still don't see it either.
Okay, thank you. Let's see if we can fix that.
I'm going to stop sharing just in case that helps.
Thank you.
Still no?
It looks like it's on its way.
Okay.
Maybe you need to double click to enter full screen mode.
It says you have started sharing your screen, but it's a blank screen so far.
Okay. Let's see. Sorry about this. I'll try sharing from Google Chrome rather than the whole screen. How's that?
Still not showing your slides.
Yeah, I don't know what I could be doing wrong. It might be a connection issue.
Uh-oh.
Stacey, can you share the slides in the background and then he can?
Yep, I will share.
Thank you very much.
Thanks, sorry about that.
And you'll just have to tell me when to switch slides.
Yeah, sure. Okay, great. Thank you. So, yeah, my name's Tom. I'm a data scientist at the British Antarctic Survey Artificial Intelligence Lab. And I've been working on a project where I've been developing a seasonal deep learning based pan-Arctic sea ice forecasting system. However, that's a bit of a mouthful, so I tend to call it IceNet for short. Now, I've been working on this for the past 9 months or so now, and it's my first time talking about it. So it's really a great opportunity to be talking to such a relevant community today. And we have a long list of collaborators and co-authors, including my supervisor, Scott Hosking, and they hail from a range of institutions, including BASS, the Alan Turing Institute, who have funded the study, Cambridge University, UCL, and the National Oceanography Centre. Next slide, please. So I'm going to start by setting the scene by comparing and contrasting from a very high level two possible climate forecasting paradigms, and that's a physics-driven approach and a data-driven approach. So the physics-driven approach is based on dynamical models. Many of you will be familiar with this approach. It's a conventional approach. And in dynamical models, the laws of physics are modeled directly, based on causality, based on hundreds of years of science, and they involve discretizing the atmosphere and the ocean into grid cells and solving coupled dynamical equations forwards in time. They're often very computationally expensive and have various limitations and biases, but are also in many ways the gold standard of what we have and an excellent tool. Next, please. So in contrast, we can also have statistical models, which are data-driven. And in this section of the slide, I'm going to talk about deep learning specifically, and also deep learning in general, because machine learning is not domain specific. So in deep learning, the models automatically learn complex, highly nonlinear relationships between variables based on huge amounts of raw data. And this is based on correlations between variables rather than causal relationships. Once they're trained, they're very computationally cheap to run, which can be useful in its own right. And just looking at the images beneath, there's a bit of a cliche here, but deep learning is inspired by the way the brain processes vision, from just detecting edges and photons to abstract representations in the visual cortex. And deep learning has done really amazing things in the past, I'd say 5 years in particular. For example, this image captioning AI, which is able to caption images. It looks like it's written by a human, a person riding a motorcycle on a dirt road, but this was actually written by a deep learning system. At the bottom, there's another famous example. Google DeepMind developed an AI called AlphaGo, which beat the world grandmaster at Go in a tournament. And Go is a much more complicated game than chess. So that's really showing off what AI can do. Next slide, please. So I'd like to talk about what data I've been using for IceNet. So starting off with the observational data I have, this is a subsection of the data. And we have time going from top to bottom and different monthly average variables going from left to right. And on the left is the sea ice data that I have leading up to September 2012. And I obtained this data from the National Snow and Ice Data Center. As well as sea ice, I also have other climatic variables, which I obtained from ERA 5. And these are reanalysis variables. So they're interpolated based on observations using physics. And I have the 2-meter air temperature anomaly, the sea surface temperature anomaly, the sea level pressure, the wind speed, and the U and V velocity components of the wind. And this only covers a period of 1979 to present, which is a lot in some ways, but also only 500 months, which in deep learning terms is okay, but not really enough to achieve the superior performance that you can achieve with deep learning. So what can we do? Next slide, please. Can you hear me?
Yes, we can hear you.
Can we get, oh, sorry, I didn't realize the slide changed. Oh, sorry, go back. My bad. Thanks. So thankfully, we also have a huge amount of climate model data. So here I've visualized data from MRI ESM 2.0, and this covers the time period from 1850 to 2100, which is over 3,000 months. in total, and that's just for one run, of which there are multiple. And you can see it looks largely the same. It won't have captured the physics perfectly, but it's close, and we can use this to our advantage. Great, thank you. And I'll also talk here about how I use the raw data in IceNet. So here I've got time going from left to right, and I have these 12 input sea ice concentration months, as well as the past 3 months of temperature anomalies and sea level pressure, as well as the past month of the wind variables. And I'm training it to output the next 6 months of Arctic sea ice. Next slide, or the next section. Great, thanks. So because of this splaying out of images taking up a lot of space, I'd like to adopt an alternative representation where they're stacked on top of each other in a cube like this. So we think of this cube of channels, of different channels of images being passed into IceNet, and it spits out this prediction of the next 6 months. But you know, if you click next, the big question mark will appear over IceNet. So what actually is IceNet? What's going on inside? Although I don't have much time, I'd like to skim over it. If you could skip to the next slide. So IceNet adopts a UNet architecture. Now a UNet is a special case of a convolutional neural network, which you'll have heard of before. So a convolutional neural network works by having the inputs to a hidden layer map to the outputs through a 2D convolution, which is shown by this GIF, where you see this small filter sliding over the image and multiplying using the overlapping patch and producing these output values. Next slide, please. So with that in mind, here is the UNet architecture, which as you can see looks a bit like a U. And I have these axes here showing that as you go down the U, the resolution decreases, and as you go along the U, the abstraction increases. And I mean that in the sense of like the way the brain processes vision, producing abstract notions in the visual cortex. Next slide, please. So these blue arrows here represent these convolutions plus a non-linear activation function that Elizabeth touched on in the first talk. And I've visualized 9 of the activation maps in this first hidden layer. And you can see it's doing things like maybe detecting land, seems to have slightly detected Greenland in one of them. It's hard to say exactly what's going on. But if you skip 2 more slides forward, you can see that as we go down the network with these red arrows representing downsampling, the resolution decreases. And if you just skip down to the bottom of the UNet in 1 more click, now we're at a very low resolution, but these represent quite high level abstract notions, such as, you know, maybe one of the pixels is activated because there was a body of hot air plus some wind blowing it in that direction, and it's predicted that to be to have moved there in the future. And if you just click forwards until we go up to the top, these green arrows represent upsampling and the gray arrows represent concatenation. So the concatenation enables us to not lose high resolution information. And in the end here, we get back up to our original resolution, and you can see these activation maps here should be reasoning about the future. So the one in the top middle looks like it's possibly predicting ice around the coastline or something like that. And if you skip to the next slide, you can see that these final activation maps are summed together to produce the outputs, and they're summed together in 6 different ways to produce the 6 different output maps. So going on to the next slide, you can see that putting that architecture away for now, there are a few gaps to fill in about how IceNet works, which I'll mention here. So there are 3 output classes, and I'm treating it as classification rather than predicting sea ice concentration directly. The reason being, predicting sea ice concentration is a harder problem, and there's noise on those values. So making it classification makes it a bit easier for the network to learn. And you can see the 3 different regions that I segment the sea ice concentration into the 3 different values: no ice, marginal ice, and full ice, which is represented in the color scheme I use in this presentation in the graphic below. Now, IceNet also has almost 11 million trainable parameters, which are all the different filters in the convolutions in the blue arrows, and those are learned through a big numerical optimization procedure that I don't have time to go into, but it's using training data by pre-training on 10,000 months of climate model data. And using the climate model, IceNet learns how to make predictions of sea ice within the climate model. However, it would have learned a slightly imperfect version of physics in that model. And therefore, I fine-tune on data from 1979 to 2015 of the observational data record. And this allows it to correct any of those biases or errors perhaps learned during the climate model. And then I hold out 3 years of data from 2016 to 18 to use as validation data. And IceNet actually comprises an ensemble of 3 networks, which is a trick to boost performance. Next slide, please. So now we can actually look at some of IceNet's predictions. So here's a case study where we start at the end of June and we predict the next half of 2017. In the bottom row, we've got the observations, so the true sea ice that was observed. In the top row are IceNet's predictions, and I've overlaid the ground truth ice edge contour with a black line to aid the eye a bit. And in brackets beneath, I have the accuracy in terms of classification accuracy. And you can see the first month, it does really quite well. As we go along to the summer months, performance degrades slightly. And then as we go back up to the winter months, because winter months are inherently more predictable, it does quite well again. And if you skip to the next slide, we can now look at the problem where we predict 1 month ahead each month. So now focusing on September, you can see it's got the ice edge really quite well here. However, it's interesting to note that IceNet can't really predict the exact breakup of the full ice into marginal ice. However, my reasoning for that is that it's because of information that IceNet doesn't see. For example, information from beneath the ocean, ocean currents and temperatures. Sorry, not beneath the ocean, beneath the ice pack. Also information on at higher resolution than a grid cell, like melt ponds, or information at less than a monthly timescale, like storms and weather phenomena. Next slide, please. And maybe skip this slide for time reasons. Another interesting output is uncertainty. So on the left, I've got the uncertainty of the predictions, because the predictions are inherently probabilities of each class. And you can see that there's a region of uncertainty about whether it's ice or marginal ice, or whether it's going from marginal ice into the ocean. But there's also a region where it's very certain that it's full ice. If you instead sum the 2 ice probabilities into one, then it becomes a binary classification problem of ice or no ice. And then that uncertainty is a bit nicer to look at, because you can see there's the uncertainty in the ice edge. Okay, next slide, please. Maybe skip this slide and the next. Thank you.
And Tom, we are running we're running short on time for a discussion. Thank you.
Okay, so I'll just finish up quickly. We can look at the lead time, the mean accuracy versus lead time. So the accuracy outperforms a persistence model at every lead time. The sea ice extent doesn't do as well, but we can perhaps talk about that in the Q&A. And then just finish off in the final slide, please. I'd just like to say thanks for listening, and we're open to feedback and collaboration and potential use cases of our predictions. So please reach out via my email. And also, we're about to submit this very soon. So hopefully there'll be a paper in a kind of proof of concept study that you can read and cite soon. All right, thanks. I'll hand back over to the ARCA staff.
Thank you. And Stacy, will you put up the ARCA slides again? I wanted to thank Elizabeth, Morteza, and Tom, all 3 of you. Those were great presentations, and asking you to cover a really dense amount of information in a short period of time. We'll now begin the question and answer session. Again, if you're joining by Zoom, please type questions into the chat window. I'll read them aloud and the speakers can respond. If you're joining by YouTube live stream, please type your questions into the live chat window, and Kuba will share your questions with me to read aloud. If you're joining by phone, you'll need to raise your hand by pressing *9 and unmute yourself. And let's see, our first question that is just a comment from YouTube, just as a reminder that those are coming through. And Christine Zinkin wrote from YouTube, "Thank you for great presentation." And then the first question from Marisa Madoff was, do the speakers as scientists generate the algorithms behind the models and visualizations, or do they work with programmers?
I could start.
Thank you.
Yeah, so So in many ways, things like a convolutional neural network or a neural network, that architecture already exists out there. And so what we're doing is changing the flavor, changing, say, how many layers and what specific coefficients we want to use, and et cetera. So in that sense, as scientists, we're doing that. In the case of designing new visualization tools, that is something my group is interested in. And so we are jointly working more with computer scientists to think about how to do that well. But I would say the majority, at least what my group is doing, we're over the hump, if you will, and we're able to do most of this work just as climate scientists trying to learn from the community rather than having a necessary collaborator. But I do think one of the perks of having the collaborators from the computer science world is I think that a lot of the methodologies and architectures out there, which there are so many, were really designed for the private sector. They weren't designed for doing science. And as soon as I start doing science with them, I realized that, I would have made this choice instead of that choice, or I wish it would do this instead of that. And so I think there is a huge whole new world out there for scientists to work with computer scientists to develop architectures specifically for science rather than private sector problems. I ended that with my opinion there. So
thank you. And a note to everyone that the speakers have agreed to stay on another 5 to 10 minutes after the top of the hour, so we can continue the discussion a little bit after that. The next question is from Muyin Wang, and Muyin says the sea surface temperatures SST example shown by Libby is using model data. I wonder if the relationship would be kept if the observed SST or sea surface temperature is used. In other words, can we use a model data to build a relationship and then use observations to make real-time forecasts? I think, go ahead, Libby.
Well, I was going to say that seems like something Tom just talked about.
Okay.
Yeah, so I think absolutely there are lots of opportunities for this, called many different things. Sometimes you'll hear it called transfer learning. Sometimes they won't associate a fancy word for it, but I think this is where, at least for the type of work we're doing, especially for subseasonal prediction and decadal prediction, where we just don't have enough data in the observations, you go to a place we do have a lot of data that's imperfect, learn what we can there, and then transfer it back to the observations and sort of fine tune it at the end to try to match observations better. I think that is a huge area, especially for climate problems, where we have a lot of data, a climate model output, although we know it's imperfect, but it gets a lot of things right.
Thank you. Let's see, I think the next question, it was back and forth between Uma and Elizabeth and Morteza, but just to reiterate, the climate research, for Arctic climate research, says Uma, we suffer from data gaps, and I was wondering if these methods can be used to fill the gap. The two of you responded, and Elizabeth, I want to note to everybody that Elizabeth shared a link to a paper in the chat that you might want to look at. And Uma responds that to do this, we create a gridded field of key meteorological variables, for instance, for fire managers. And depending on what, I'm sorry, then I believe it was, the response there is depending on what you mean by data gaps, there are generative models. Would either of you like to, Libby or Morteza, expand on that? I think that.
Libby can go first, if you don't mind. Just keeping the order.
Yeah, so there are certainly, like, gap filling is something in the private sector. If you just YouTube, gap filling of like faces, it's very entertaining. You could be sucked in for hours. But that concept applies to climate as well. We have missing data. How can we learn from other data, how the relationships, say, across the globe, so we can fill in the data that's missing? There are already examples. I posted one for climate, for surface temperatures. But there are, I know of many other people working on this problem at all scales, not just the global scale, but also very small scale gap filling. So my feeling is this is an exciting area, and there's a lot of work being done, so you don't have to reinvent the wheel.
Thank you. Risa Madoff again asked, can machine learning model deal with multiple spatial scales?
Kind of depends what exactly you mean by that and what form the data comes in. So if it comes in image form, then convolutional networks can absolutely handle multiple spatial scales. So from the diagrams you saw of the convolutional neural networks in these presentations, the first layer often extracts small scale features. And then as you go down the network, it turns out that through the successive downsampling and convolutions, the receptive field increases in size, and therefore the hidden layers further down are able to deal with features and objects that are larger in size. And then I'll just labor the analogy of the visual system. That's a similar thing that happens in the brain when we process vision. So it depends exactly what you mean, but kind of yes is the answer.
Thank you. CC Bits asks, can you think of ways to combine machine learning to bias correct the predictions of dynamical models?
So I'm also happy to cover that. So definitely, yes, I think so. You would need to change the outputs of your model to instead of being predicting the value directly, train the network or machine learning model to predict the error. And then you simply run your dynamical model, and then you add on whatever the neural network has predicted as the error. And then hopefully that should improve performance and predictive skills slightly. And it should learn to identify what features in the inputs lead to errors in the dynamical model. So I think there's a lot of opportunity there.
Thank
And
you.
I want to add that we do this already, you know, just general bias correction. We know our dynamical model maybe is too cold somewhere, so we always add a little bit after it outputs. So we do this already in this sort of post-processing, these post-processing steps. And I think what machine learning is going to add is just, especially if you have the data, the nonlinear component of really getting at regime dependence in these errors. I think that maybe current methods it's harder to capture.
Thank you. Another question for Tom from Bill Merrifield is, Tom, have you compared correct classifications to those obtained from simple forecasts based on recent climatology, et cetera?
Yeah, so I don't know if while I quickly answer that, Stacey or anyone could bring up one of my final slides from my presentation that I had to kind of rush over. So thank you for asking. But yeah, I compare with a persistence model, which many people will know, but essentially you just copy the sea ice month from the year before and use that as your prediction, which is very, very simple, but actually a surprisingly strong benchmark because of the cyclic nature of sea ice. So I've used a number of benchmarks, including a kind of linear trend looking at the past 5 years and trying to extrapolate the linear trend at each grid cell. I've looked at a dynamical model, ECMWF-C3S, but so far none of them actually beat the persistence model. So I thought for this presentation, I'll just only leave in slides comparing with persistence. And if you just skip forward 2 more slides, please, you can see the mean performance across the held out validation set with persistence being blue and IceNet being red. And the accuracy there is above persistence at all lead times. But I want to try a stronger benchmark if there is one out there.
Thanks. We've got a couple minutes here. What I think we'll do is invite people to take a look at the closing slides that we have, and then continue discussion for another 5 or 10 minutes after the top of the hour. Stacey, could you share the slides, the thank you slides, and invite people, we'll also invite people to provide information about the link for the Survey Monkey. So we do welcome your feedback, and we would really like to have any input you have about the evaluation of this webinar, and also information about future ideas for future seminars. And I believe the link is now available in the chat window from Britt Myers. It's surveymonkey.com /r/SIPN2. And again, we'll be recording, this webinar has been recorded and we will archive it on the ARCIS SIPN page. And that information will be included in the follow-up email to everybody that registered online. So thank you all who are needing to leave here at the top of the hour. For those of you who can stay, we'll continue with the question and answers. And I believe the next question is from Mitch Bushik. Oh, I'm sorry.
Betsy, can I go back to a question about, I mean, it was an early on question and I think it's worth important. You know, we haven't really been talking about the limitations, and I think that's important. You know, right now we're lucky that the two case presentations that we had today, you know, Earth models output enough data to kind of provide some basis and then fine tuning on top of that. But when we don't have that, you know, for instance, we're looking at the some glacier discharge, and a lot of variables that we need are not resolved by Earth models, either the resolution or other issues. So when we don't have that kind of data, what do we do? I think those are really important things to consider as you approach your problem. The other one thing that I wanted to answer about whether we use the visualizations that already exist, no, we actually, those took a lot of time and money to build. And that's where the risk is. And there are programs that support these kinds of tools generations. So again, this NSF EarthCube award will help us create those kinds of tools for you, you know, in collaboration with computer science. I live between computer science and geography. So the visualizations, if they're custom, they are really expensive and time consuming to build. That's a consideration to have before going into the problem. But one, I think one of the key questions that was there, do these algorithms exist? A lot of them do. Scikit-learn, Python, etc. They are in there if you want to just lay out an architecture of a deep learning model and then do training and testing. But then just bringing physics into it would be something that is quite a headache, right? Right now, the cost functions only look at the training data and try to minimize the prediction error. That's about much you know, they do through backpropagation. But again, what if you don't have enough data, but you are all scientists and you are aware of the processes underneath, and if you know of a cost function that should be in place, even without enough data, then adding that physical constraint to your model is something that people have started investigating, and I think it's a really interesting direction to take for this community. So I just wanted to add that. When I saw that early question, I didn't have a chance to talk.
Thank you. We have another, let's see, a question from Alexander Araro. Thank you for the excellent presentation. How might any of the presenters' research intersect with, for example, machine learning developed by autonomous vehicle operations at the ice edge, particularly where data throughput is incredibly limited? Alternatively, are any of you working with data sets generated from ASVs?
Yeah, so I haven't worked with data like that before. There are certain algorithms that lend themselves to sensor networks. I don't know exactly what the application would be. One possible intersection is, I don't know if you saw the slide on uncertainty in my model. You can see that certain regions have higher uncertainty than others, and it's possible that there's something to learn about where you should put sensors to make the data as high quality as possible in those regions. But that's just a kind of secondhand thought on that topic.
Thanks. I have a question then from Mitch Bushik, who asks, how do we deal with the quote out of sample end quote issue? Future Arctic conditions will occur in different state space than the past training data.
So I can quickly hop on that as well, which is that because of IceNet, my model being pre-trained on climate model simulations running from 1850 to 2100, it's seen all these different regimes of sea ice behavior within the model. So it's seen far into the future when, unfortunately, we're getting Arctic ice-free summers almost every summer. and that lets it understand where it is on the trajectory a bit better with the observations.
Thank you.
So I think Tom's answer is great, and I think that. But another is this idea that Morteza was talking about, this physics guided machine learning, or knowledge guided machine learning, or whatever acronym you want to give it. So as scientists, we know certain physical laws exist in the data or in the processes we're studying, and so if there are groups studying how to put that information into these models, and if you can really get your machine learning method to learn the right relationships for the right reasons, then unless physics breaks into the future, the machine learning method should also be able to move forward into the future. Now that's a big task, don't get me wrong, but if there's a few very key physical equations or relationships that and you can get into that model, it might help you extrapolate or go out of sample as we move into, as we continue into the 21st century predictions.
Thank you.
I'd echo that sentiment. I think although we're starting to see more and more data science being applied in the climate environmental science domain area, which is really cool, the most interesting stuff I think is more in the intersection. And while there's a lot of low-hanging fruit to be used in just applying basic machine learning algorithms to data that's been untouched by these really advanced algorithms, there's a lot of really interesting stuff that can be done at the intersection of the two.
Thanks. And I want to draw everybody's attention to a note from Zagam early on with a link to a personal website that generates image of people that don't exist with the help of GANs. And then Molly, Michelle Wernigja, I believe I've mispronounced your name, asks Tom, for Tom, I appreciate your explanation of how observations can be used to fine-tune the training of the model got from the climate model output. I'm curious if there are, or if you've considered any other alternatives that might involve the observations directly in the training process.
Yeah, thanks. So I've interpreted this question possibly incorrectly, but I've interpreted it as how can you get more training data from a limited set of samples, assuming there's some other variable that you might want to predict. I don't know what it is, sea ice thickness or something like that. Let's say it's not captured in a climate model, because that would be a good approach to take to use transfer learning. What you can do in that case is use data augmentation, which isn't going to work in every application. It would depend on the specificities of the application. But data augmentation involves things like manipulating the inputs, assuming they're images, like rotations, changing the scale, flipping. And although that's more common in commercial applications where you're trying to detect a dog or something that can be in any position, it's possible that there's something that you can get out of a climate data set using a similar approach. But it really depends, but it's a great question.
Thanks. And then CC Bits made a comment thanks Tom and Libby, it seems like machine learning could do a much better job than linear regression and maybe deal with more variables. And Elizabeth responded to that saying, agreed. Of course, you don't get something with nothing. And so the trick is that you need enough data to train/learn on, and in order to learn those nonlinear relationships. If you have only a small amount of data, linear regression may be the best you can do. Would you like to expand on that? I'm reading these because I know that the folks that are joining by YouTube cannot read the text in chat. Elizabeth, are you still with us?
Yep, I'm here. I think my point is always when people bring up, oh, this could be better than linear regression. I can give you lots of examples where linear regression is the best we can do. And it just suggests that either the relationship actually is linear, in which case linear regression is the way to go, or you just don't have enough data. And when you don't have enough data to learn all the intricacies of some very, very complex relationship, linear regression can be the best you can do. And so just reminding everybody, as Morteza said, we haven't really been talking about limitations here, and it's really important. You need data to train these things, and the more complex of a relationship you want learned, almost certainly the more data or the smarter you're going to have to be with how you set that up. And so just reminding everybody that this isn't the solution for everybody's problem. It's really one solution that may work sometimes.
Thank you. And a final comment from that I see from Mitch Bushik is that he says, thanks, Tom and Libby. I like the idea of using physically based constraints to limit spurious results associated with model biases. I believe that that's it. Are there any other questions coming from the live stream service, Kuba? And if not, I believe we've answered everybody's questions. I would ask the presenters to stay on a little bit longer. There was then after we close, but other than that, I believe we're ready to close the webinar, seeing no other questions coming in. So I want to go ahead, Kuba.
No other questions from the YouTube live stream.
Thank you. Then we will conclude today's webinar. Again, thank you very much for everyone for joining us. I think there was great discussion. The presenters did an amazing job of providing very dense material in a short time, and I think that was extremely useful. Really appreciate their work. We will archive today's presentation, and it will be available on our website, arcus.org/SIPN/meetings/webinar.